welcome everybody to a new semester and a new series of the Heidelberg Joint Astronomical Colloquium. As I always say, this is definitely the place to be on a Tuesday afternoon, and thanks to everybody who's come trudging through the wet puddles outside. Because the reason this is such a hot place today is that we will have one of the experts in the field which recently Heidelberg has almost been dominating worldwide, which is the measurement and interpretation of multi-wavelength images of nearby galaxies. So thank you, Mélanie, for agreeing to give this talk. We very much appreciate that. Now, Mélanie did her PhD in astrophysics at the University of Paris in 2016 under the supervision of Susanna Madden. And directly afterwards, she moved here to the Institut at the University of Heidelberg, where already she was doing, really leading published works on star formation feedback mechanisms based on observational evidence of galaxies. And that's now accelerating into the era of JWST. And on the basis of her work and the future prospects of this really expanding field, Mélanie was awarded an Eni Mota group leadership position here at ITER Institute, where that was last year, and that group is just beginning to impact on the field. And the topic of the talk today is the cloud scale baryon cycle across the nearby galaxy population. So Mélanie, please take it away. Thank you very much.
Okay, thank you very much, Richard. So I'm very happy to be here today, this afternoon, to talk about how galaxies evolve under the influence of the cycle of star formation and feedback within them. And I will show you during this talk that with recent high-resolution multi-wavelength observations and state-of-the-art simulations, we are now making revolutionary steps in understanding this cycle of star formation and feedback. Right. So let's start. What do we see when we look at a galaxy? We see gas and stars. And this gas is organized in an extended reservoir of diffuse interstellar medium, within which we find denser structures, which we call molecular gas clouds. This denser structure, under the effect of gravity, contracts, and within them, within the densest parts of these clouds, stars will start forming. Throughout their life, stars emit radiation and winds, and this progressively disperses the remaining gas. This is what we call stellar feedback, and I will talk a lot about that in this talk. But really, the conversion of gas to stars in galaxies is a cycle. And you can see that in the simulation here, where you can follow an overdensity of gas as it contracts, form stars, which you don't see in that simulation, but you see the effect of these stars. You see this bubble that are being blown out under the effect of stellar feedback. So the big question that we're trying to answer, how do galaxies turn their gas into stars? How do the newborn stars impact the remaining gas? And how does this cycle depend on the galactic properties and environment? And this is what I'm going to try to address during this talk. Schematically, let's go back to something very simple, a schematic of this cycle. So we can describe it as follows. You have gas accreting onto galaxies in the diffuse interstellar medium. Then under the effect of gravity, clouds will form, assemble, and still under the effect of gravity, stars will form in the densest part of these clouds. During their life, they emit radiation, winds. At the end of their life, some of these stars will explode as supernovae. So under the influence of stellar feedback, these dense clouds are being dispersed and the gas will be recycled into the diffuse interstellar medium. Note that these clouds, these dense clouds, can also be dispersed dynamically from the galaxies. The combined effect of the stellar feedback makes that some of the gas will be ejected out of the galaxies in these galactic winds. And then this hot gas will progressively cool down, reaccrete in the galaxy, and this cycle can start all over again. What we're really trying to understand here is how this cycle works, and in turn, precisely how the mass flows are going through this cycle, through each part of this cycle, a bit like the carbon cycle on Earth. So we're trying to put basically values, numerical values for each of these arrows here. What is the mass flux of the gas from the diffuse interstellar medium going into the molecular clouds? How much mass and how fast is this dense gas converting into stars? So really what these equations mean is that they're mass flows, which means it's a mass divided by a time scale. And all of these arrows you can describe as such. The masses are typically relatively easy to measure. Okay, easy, quote unquote, but through luminosity, you can normally calculate the mass. But the timescales are quite difficult, and I'll talk about that in a few moments in my talk. But first, how do we manage to calculate these mass flows through to describe this cycle? We can do that in two different ways, as is everything in astrophysics, either through observations or through simulations. But both of these approaches are facing major issues. Let's start with simulations. The problem here is that star formation happens in a cosmological context where all scales are connected, and they cover a wide range of temporal and spatial scales. So the accretion of gas onto galaxies is what is illustrated here by this simulation from the Illustrates team. You can see the galaxies in blue and the cold gas falling in onto these galaxies in green. So you can see that it spans 10 to the 5 kiloparsecs here. You need to zoom in by several orders of magnitude to find one galaxy. Within these galaxies, within this galaxy, you even have to zoom in by several orders of magnitude to find one star-forming region, within which, again, several orders of magnitude smaller, you find these very dense clumps within which stars will form. And again, it's several orders of magnitude smaller that you will find the formation of a single star with its protoplanetary disk. And all of these scales are connected by feedback where energy is injected from the small scale to the larger and larger scales. So it's 12 orders of magnitude here that you have to cover in distance if you want to simulate the cycle of star formation and feedback through first physical principles. And that's not all. It's also in terms of temporal scale that you cover here 9 orders of magnitude between the explosion of a supernova and the time scale that you need to simulate if you want to see galaxies evolving under the influence of this cycle. So to summarize, trying to model, to simulate this cycle from first physical principle is computationally not possible at the moment. And this is a huge problem because this means that we need to use sub-resolution prescription. If I just go back to my previous slides, this means that if you want to, let's say, simulate a galaxy with the regions of star formation within them, you need to cut here at some scales. And the rest will be sub-resolution, and you need to make assumptions with sub-resolution prescription to describe these scales. And these sub-resolution prescriptions are unconstrained observationally. What you see here are 3 simulations with identical initial conditions. The only thing that changed is the sub-resolution prescription for which gas is forming stars. Is it the molecular gas? Is it the gas above a certain density threshold? Or is it the gas that is only the self-gravitating gas? Okay, so again, 3 galaxy simulations with identical initial properties, but different gas criteria for which gas is forming stars. And you see that the result leads to completely different properties and structures even of these galaxies. So really, these uncertainties on the sub-resolution prescriptions dominate galaxy evolution simulations. And this is true for star formation, but also for the prescription for feedback. You can see that if you adopt supernova feedback or only photoionization or combination of both, you have very different, again, for identical initial conditions, it leads to very different properties and structures of the simulated galaxies. And all of these choices make sense physically, right? But you need, if we don't know which one is the correct one, we cannot say which of the simulations represents really the real universe. So, okay, from simulations, it seems a little bit difficult to be able to recover all of these mass flows. So let's try from observations then. We now have wealth of different observations from ALMA, MUSE, HST, James Webb, SDSS, and combined, all of these observations allow us to image at great sensitivity and resolution all steps of this cycle. So we can go ahead and try to measure these mass flows from the simulation, from the observations. But again, this is very difficult here because what we see from observations are fixed snapshots instead of a nice movie like in the simulations. So the time evolution cannot be measured directly from the observations. It's as if I were to stop this simulation here, and without telling you what happened before, I'm asking you to guess what will happen after. Well, this is quite challenging. Fortunately, we recently have observational breakthroughs that now enable us. It's me.
The microphone banging.
Okay, that now enable us addressing these challenges. So we have new cloud scale observations with FANGS in particular, the FANGS survey, in which Heidelberg is very active on. And we have new analysis tools that have been developed later, especially by Diederik Krausen and Steve Longmore in 2014. And I will talk a little bit about that afterwards. But what are these observations first? With the FANGS survey, we have been able to recently image all parts of this cycle, from the atomic gas, the molecular gas, the dense gas, the first stages of star formations, heating the dust and the gas around them, the ionized gas, and the young stars and clusters themselves. So that is a combination of many different surveys, many different instruments, dozens of hours of observations that allow us, plus some complementary data, that allow us to image at high resolution all parts of the cycle. And combining these cloud scale observations with these new analysis tools, we now have pioneered the first timescale measurements with a lot of involvement from people here from Heidelberg. So with Diederik Krausen, Jacob Ward, Jaeon Kim, we have made this first timescale measurement, which allow us, in principle, to overcome challenge 2, measure the time dimension from fixed snapshots of the observations. If we now can measure the time dimension from the observations, it means that we can have constraints to provide to the simulations, input from the simulations. So that overcomes challenge 1. And I'll touch on that a little bit at the end of my talk. But the fact that we have all of these observations now raises a third challenge, is that this analysis currently requires human intervention. And with so many data, it is currently very difficult to do that for more than 100 galaxies with multi-wavelength observations. So I'll say a bit more at the very beginning of the talk. But now let's dig into this timescale measurement. How can we measure this time for each of these arrows here? This is really a critical question because these timescales are of the order of several millions of years. So you cannot sit there, look at a cloud and expect it to form stars and measure how much time it takes. So this has been really a long-standing problem. Several studies have suggested cloud lifetime of more than 100 megayears, based on the fact that you have molecular clouds between galactic arms in galaxies. Some further studies have measured cloud lifetimes of 10 to 50 million years based on classifying the clouds. So how many clouds do you have without stars? How many clouds do you have with a bit of star formation? How many stellar associations do you have that are not associated with clouds? So counting these different classes will tell you approximately how long each of these phases lasts. And finally, based on looking at the gas orbiting the center of our galaxy, also several studies have measured about 1 million years for the cloud lifetime. So you can see that there is 2 orders of magnitude here. So that's very uncertain. Are these variations actually physical? Or because we're looking at different environments? Or do they just come from different experiment designs and subjective cloud classification, for example, in this second case here? So to try and answer this question, let's take a step back and answer a very fundamental question with 2 extreme cases, basically. Do clouds live for much longer than massive stars, or do they live for similar timescales? In other words, do we have a quasi-equilibrium between gas and stars, or do we have a rapid cycling? Observationally, what would you see? In the case of quasi-equilibrium, clouds would form stars for many dynamical time, which means that gas and clouds would be correlated on the small scales. If you have a rapid cycling, clouds are destroyed very quickly as soon as they form massive stars. So gas and stars are expected to decorrelate on the small scales. Now that we have really good high-resolution observations with ALMA, for example, we can simply go look at a galaxy and answer this question. What do you see here? This galaxy, you see H2 regions in red and molecular clouds in blue. Well, you see very clearly that some H2 regions have no gas associated to them. Some molecular clouds do not have stars associated with them. So we see a decorrelation between gas and clouds at the small scales, which means that we have a rapid cycling between gas and stars. But how can we quantify this rapid cycling? How can we put numbers on this timeline? For that, so Diederik Kruisen and Steve Longmore here have developed this quantitative method to quantify this decorrelation and translate it into an accurate measurement on of the cloud lifetime. To do that, we can measure the gas to stellar flux ratio on this entire map, and you get a galactic average. Now, if you do that on much smaller scales, just focusing on molecular clouds, you have the gas to stellar flux ratio when you focus on gas that is higher by definition. Now, if these small apertures, you focus them around stars, the gas to stellar flux ratio is going to be lower than the galactic average. You can do that for many different sizes of apertures or different resolution. And you start seeing this characteristic shape here, where you actually see the decorrelation on the small scales when these 2 branches start to separate. It turns out that this behavior, this decorrelation, can be entirely described by 3 independent parameters. The cloud lifetime that controls the asymmetry between the 2 branches, the feedback timescale that controls the flattening of the 2 branches, and the separation scale, so how far apart different regions are in the galaxy. And this controls when these 2 branches start to separate. So by fitting this analytical expression to the observations here, to the gas to stellar flux ratio as a function of size, we can directly measure how long gas clouds are living, how long it takes for the stars to disrupt the gas, and how far apart these regions are in the galaxy. So we now have an objective and systematic measure of the GMC timescale. Let's apply that to an example. So this same galaxy I was showing before. So now these are real data. We measure the gas to stellar flux ratio when we focus on gas peaks. or when we focus on stellar peaks as a function of the aperture size. And you see this very clearly, this decorrelation here, that is a characteristic feature when you have a rapid cycling. By fitting these observations, we measure a gas cloud lifetime of 11 megayears. This is pretty short. This is really close to the free fall time, and I will come back to that in a moment. The feedback time is 1.5 megayears, again, pretty fast, before the first supernova typically explodes. I will come back to that later. And all in all, this measure of timescales allow us to measure the mass flows along the matter cycle. Now that we have both the masses and the times, we will be able to constrain the physical processes regulating this cycle and further our understanding of the galaxy evolution. So let's go ahead and apply this measurement first to this arrow here. So I want to calculate the cloud lifetime here to be able to measure this mass flow. So for that, this is the work that has been done by Jaeyoung Kim. She has just finished her PhD in Heidelberg at the beginning of the year. She's now a fellow in Stanford, and she has applied this measure of the statistical technique to all of the FANGS galaxies. And the first thing that you notice here is that for all of these galaxies, you see this characteristic shape here with this decorrelation of the two branches, which means that you have a rapid cycling between gas and stars. So not only in one galaxy that I showed before, but in all of the galaxies that we've looked at. By fitting these observations, Jaeyoung has derived the timeline, the evolutionary timeline, so from gas to stars, for all of these galaxies. And let's focus for now on the lifetime of the clouds. So it's between 5 and 30 megayears. You have a range for different galaxies, as you can see here. As I mentioned before, this lifetime is limited to a few dynamical times. So if you compare this cloud lifetime to the cloud freefall time, you can see that these galaxies are typically between 1 freefall time and maybe 3 freefall times. So by and large, the clouds are mostly falling under, contracting under their own gravity before they start forming stars and getting destroyed by them. This cloud lifetime is also environmentally dependent. It's not the same in all galaxies, and we have hints of why this might be happening. The first thing that we have noticed, or one example of what we have noticed, is that you have longer cloud lifetime when you go to more massive galaxies with higher gas surface densities. But this is very much still work in progress. And in fact, this is the work that Andrea Romanelli is conducting here in Heidelberg. And he has started first to look at how this cloud lifetime might be varying within galaxies between arms, spiral arms, and interarms regions, because there have been suggestions that spiral arms might be triggering star formation. And what Andrea has noticed is that if you decompose this galaxy into arms regions and interarm regions, you measure the cloud lifetime and the feedback timescales in these two regions, you notice that, well, you don't notice any difference between the distribution of cloud lifetime in the spiral arms in yellow or in the interarms in blue. Same thing for the feedback timescale. So there is no statistical difference from the cloud evolution, whether you're in the arms or in the interarms, and this is quite interesting. However, there is a dependency of this cloud lifetime with galactocentric radius and cloud properties, and this is work in progress by Andrea. Now let's go back to our timescale. Maybe something that you have noticed here is that for these 5 to 30 million years of the cloud lifetime, a lot of it here is orange. That means that no stars have started to form yet. It's about 70 to 90% of the cloud lifetime that seems to be inert. But is that really correct? We have been imaging the formation of stars in a Jaeyoung study using H-alpha. But we know that H alpha in some region here, you might not see H alpha, but you might see the very young stars in the infrared. So these stars are very young, they're still embedded behind dust and gas, so we don't see them in H alpha. But so we can maybe add here an additional step of embedded stars and image that step using infrared emission. And the first part of this study has been done by Jaeyeon using Spitzer observations. And she has shown that indeed, for 1 to 4 million years, there is star formation within these clouds. So they're not completely inert before we see the H alpha shine. Pre-James Webb, that was only 6 galaxies. Now we can do much more. With the James Webb, we now have within the Funk survey 19 additional galaxies already observed, and more data are coming because we just had a cycle 2 James Webb approved for 55 more galaxies, so the entire Funk sample. And so Liz has been working on applying this technique to measure for how long stars are embedded within gas clouds using the James Webb data. So you go from 6 galaxies to many more. This is not even the entire sample yet, but already we can draw some conclusions. The first thing is that, yes, these clouds are not completely inert, but it adds maybe between 0 and about 2.5 or 3 million years to the phase during which they're forming stars. So there is still a long part of the cloud lifetime that is inert. Again, this duration of obscured or embedded star formation seems to be environmentally dependent. We see a hint that it decreases slightly with increasing star formation rate. So if you form more stars per unit area, then the gas is being cleared faster. So to conclude this first arrow here, we've been able to measure the cloud lifetime here. So it ranges between 5 and 30 million years. Now we can move on to the next arrow, stellar feedback. How fast are clouds destroyed? So we could see that here already on that time scale, that clouds are destroyed pretty quickly, between 1 and 5 million years. And this is consistent with what has been already shown in a couple of targeted galaxies with very high resolution, where you see that young clusters, when they reach the age of 3 to 5 million years, they are cleared of gas. So they are not associated with gas anymore. Again, this phase of cloud destruction is environmentally dependent. So you have a time scale for cloud destruction that is longer when the density contrast in galaxy is low. So that means that if the gas clouds are isolated and then the medium around them is very diffuse, you can destroy them very quickly. If the gas clouds are embedded in a relatively dense medium, then it becomes harder to disrupt these clouds. The fact that this destruction phase is so fast means that the star formation efficiency is limited. You don't have enough time to convert a lot of gas into stars. So it's only 1 to 8% of the gas that is converted into stars. And again, this is consistent here. So these are the observations. It's consistent with this data point here that comes from simulations. But how do we know that the clouds are actually destroyed? Maybe we don't see the clouds associated with the stars because the gas has been pushed away, but it's still there. So that is a scenario that has been put forward or explored in detail in a recent paper, and that's why I would like to investigate that a bit more with you. So we have 2 scenarios here. One, the cloud is dispersed. So with time, you form stars, and the stars will disrupt the gas, and the gas will be, the clouds will be gone. The second scenario is that the gas is pushed away. You have a separation, a physical separation between the cloud and the stars, but the cloud is still there and can continue forming stars maybe further away. So how can we distinguish between these two scenarios? At high resolution, it's actually very difficult. But let's look at that first. So if you put an aperture, you know, we're putting apertures at several places in the galaxies. If you put an aperture around these cloud-forming stars, you will classify it as an overlap region. You have both gas and stars. Around this region, it's isolated stellar region. And same thing here. For the drift scenario, you put in a small aperture here, you missed the gas, so you classify that as an isolated stellar region. Now, so this doesn't allow you to distinguish between these two scenarios. But now let's actually degrade the resolution of our observations. Let's put a large beam on top of this. Now, if we do that, in that case, in the feedback, in the dispersal scenario, because the gas is gone, if you include a larger part of the galaxy, there is still no gas. So you still have an isolated stellar region. On the drift scenario now, if I increase the aperture, I'll start capturing, again, this cloud here that has been moving further away, but not that fast, maybe at 10, maximum 20 kilometers per second. So it's still nearby. If I take a larger aperture, now I see both gas and stars in that beam, so I can classify these regions as an overlap region. That means that in the dispersal scenario, the feedback phase is, the duration of the feedback phase is constant with increasing beam size. But in that scenario, in the drift scenario, because I now start counting more overlap regions instead of isolated stellar regions, the duration of the feedback phase will be artificially increased with increasing beam size. So if I represent this as a little schematic here, showing the feedback timescale as normalized by the high resolution value as a function of resolution, if the cloud dispersal scenario is correct, it stays constant. If the drift scenario is correct, I will see an increase of the feedback timescale with increased resolution. So now what is it in the observations? We now have a couple of galaxies where we can actually do that. We can probe these scenarios. And I'm showing the four galaxies here, 4 examples where this is indeed possible. So the drift scenario would be following this rising curve here, and the dispersal scenario would be staying flat. And you see that in these 4 cases, the dispersal scenario is favored over the drift scenario, both globally and for individual galaxies. Maybe NGC 300 is a little bit more in between, but if you actually look at the error bars here, and it's just between these two lines. After that, the uncertainties become too big to draw conclusions. So you just need to look in between these 2 lines. Again, it's the dispersal scenario that is favored. So we can say that clouds are being destroyed or dispersed during the feedback phase, and it's not a simple drift. But now what mechanisms can actually disperse the cloud so quickly? There are 2 classes of mechanisms that you can look at: external processes, so turbulent flows, shear, spiral passages, or stellar feedback. And I will focus on stellar feedback in the next few minutes. So jet and outflows are a little bit particular here. I just mentioned them for completeness, but they cannot disperse the giant molecular clouds, only the dense small cores. Supernovae, so one scenario, one mechanism, ionizing radiation, stellar winds, and radiation pressure. They all act on different timescales. So these are the timescales. I will not go into the details of these equations, but it's good that they act on different timescales because we can measure observationally what is the timescale of destruction. So let's compare what is predicted for each of these mechanisms to what we observe for the cloud dispersal time. And before I show you the data, I want to mention that this is the one-to-one line here. So if the data points are above the line, the predicted timescale is longer than the observed one, meaning that this mechanism is too slow to explain what we're seeing. If the data points fall below the lines, it means that the mechanism is fast enough. It can destroy the clouds as fast as we see in the observations. If we look at what we predict for supernovae, for these galaxies, you see that for most galaxies, the data points are above the lines. So supernovae arrive after the cloud has already been dispersed. If we look now at the other mechanisms, so winds, photoionization, and radiation pressure in a, but this is less strong, you see that this can explain why the clouds are destroyed so quickly. And actually, what you see is that the prediction is smaller than the observations, which means that theoretically, the clouds could be gone even faster than what we see. But this is not necessarily a problem. What it means is that the coupling efficiency of the feedback mechanism with the gas is not 100%. So some of the energy is lost without affecting the gas. And this is what you see also in simulations. So this is a simulation of a cloud forming stars in blue. And you can see that after some time, you have these big holes here. You have these cavities, and energy, photons can leak out through low density channels out of the region without affecting the gas anymore. Again, if I look at this coupling efficiency, so this is now 1 minus the coupling efficiency. For simulations with the stars here, it is quite consistent with what we're seeing from the observations. So pre-supernovae feedback are important to destroy the clouds, but now is it radiation pressure or ionization or winds? This is still not clear. And what has been concluded from previous studies focusing on just a small number of galaxies is that this dominant, mechanism is actually the dominant one, will change with evolutionary stage. So radiation pressure dominates for young H2 regions, while in evolved H2 regions, photoionization pressure will dominate. So you have a change of which mechanism, feedback mechanism, is the most important with time. And that might also be true with environment, although this is still a bit more difficult to do when you look at further galaxies that are further away where the resolution is not yet sufficient. But there is a hint that this mechanism might also vary with environment. So in conclusion of this short cloud destruction phase here, you have early feedback that pre-processes the gas before the supernovae explode. And that means that when the supernovae explodes, and you have some examples here of supernovae remnant, the gas is already gone, which means that the energy from the supernovae can affect much larger scales in the galaxies than if they were confined in dense gas. So far, we've been able to measure the cloud lifetime between 5 and 30 megayears, the feedback times between 1 and 5 megayears, and a star formation efficiency of 1 to 8%. Now we're left with this arrow here. So what is the timescale for the formation of the clouds? And for this, you need to have H1 observations. And this is quite challenging to have H1 observations at high resolution. But this is possible for the LMC, for example, which is a very nearby galaxy, our nearest neighbor. So the same method has been applied to H1 observations. And you see here this sort of movie that is reconstructed the timeline for the formation of dense clouds from H1. And it takes a very long time, as you can see here. You see the real rotation. And if I start the movie again, that's not going to help. Okay. So you see the real rotation of the LMC that has been observed with the Gaia observations, and it takes now double the amount of time to form dense molecular clouds from the H1 observations. Maybe I can speed things up a bit. So when you do the measurement, you have 48 megayears for the atomic cloud lifetime in the LMC, which is consistent with the predictions from galactic dynamics. We hope that in the future, with the future SKA, we'll have many more high-resolution observations, and we'll be able to do that in many more galaxies. So great. Now you see CO appearing. After a very short time, you see 24 microns, so embedded stars, and then H alpha is now shining, and then you see all the ionized gas lines. So after this long time of cloud formation and assembly, things are going pretty fast. So have we changed this challenge too? Have we been able to measure the gas flows through this cycle? It seems like it. We now know that clouds are efficiently dispersed by stellar feedback within just 1 to 5 million years. Their lifetimes is limited to a few dynamical times, between 5 and 30 megayears. It limits the star formation efficiency to just a few %, and it allows supernovae to impact large scale in galaxies. Of course, this is not the end. We still have lots of challenges going forward. I've talked a little bit already about the environmental dependence of the matter cycle. So we need more observations covering different morphological types. So early type galaxies, CMZs, but also different moments in cosmic history, up to redshift 1 or 2. So this is work in progress. We also need finer time resolution. Of course, what I've described until now is we got H1 cloud, then molecular clouds, then stars. And that's skipped a lot of detail steps in between. And for that, we need multi-wavelength observations. We already have some of them in hand. So with MUSE, with James Webb, I've talked about the embedded part of star formation. We also have AstroSat. So again, this is work in progress to improve the time resolution of this timescale. So we have put all of this together. So these new cloud scale observations with new analysis tool to overcome challenge 2. Now we can use these measurements to improve the simulation, the description of the feedback and star formation in simulations. First, one thing that we can do is already test whether the simulations, the subgrid physics used in simulations reproduces the observations or not. And I'm here comparing the GMC dispersal, the cloud dispersal time as a function of freefall time. And you see that the simulations are here in color dots and the observations here are in gray. The agreement is not amazing. Several things that we can, several conclusions that we can draw from this. We know that there is obscure star formation that has not been taken into account in these observations. So it will increase, it will raise these points by the amount of these black arrows here. So not bring it yet to the simulations, but a little bit closer. Now, another thing is that we have beam dilution in the observations. So all these points are probably a little bit moved to the right there. So again, you could move there a little bit to the left, get a bit closer to the simulations. And the third element is that we know also that there is missing physics in the simulations. So let's have a look at that. How do we know that? Well, we have tested the decorrelation. Remember at the very beginning, this decorrelation between gas and stars in galaxies that we see in all galaxies that we have observed so far. Now, do we see that in simulations? We have taken this simulation here by the group of Mark Rummels. It includes feedback from supernovae and photoionization, so quite detailed. All macroscopic quantities, so star formation rate, gas mass, depletion time, and cloud properties, so cloud radius, velocity dispersion, etc., are consistent with the observation. So it's a very good simulation. But the matter cycle is not at all consistent with the observations. If you compare the decorrelation that we observe for observations with what we see for simulations, you see that these two branches are very flat. It means that there is no decorrelation between gas and stars. There is not this rapid cycling between gas and stars. In the simulations, clouds are sitting here forming stars for several tens of millions of years. And this is not what we see in observations. So this test can be used as a fundamental test of simulations. And I'm showing here a couple of, it's kind of a busy plot, but the observations are shown in gray and black, and simulations are shown in color. So this one is the one I just showed, that you can see that they're not a good match between the simulation and the observations. An improved version of this simulation is in yellow. You can see that you have a little bit more of a decorrelation, so you're getting there. And now is the simulation of Semenov et al. In blue, which this one in dark blue includes radiative transfer. It's also very high resolution, lots of physics included. And now you see that you have a very good match. You start having a very good match between the simulation and the observations. So you can test whether the physics included in the simulation allow you to reproduce this cycle. So this is one, so to get the simulations closer to the real universe, there are traditionally two approaches. One is to fine-tune the parameters of your simulation until you get what you want. The other one is to model from first physical principles, which is very difficult, very expensive computationally. So we have developed a third approach, which is to rely on the observations and to add the effect of feedback, what we saw in the observations, this rapid feedback, this rapid disruption of the clouds, to add that as an additional momentum in the simulation that just included supernovae. So does this work at all, to rely directly on the observations? Actually, it works pretty well. So the star formation rate per unit gas mass is consistent with observations. And I'm showing here the star formation rate as a function of time for a simulation that includes only supernovae and one that includes supernovae and this early feedback motivated. So EMF stands for empirically motivated physics. So included the feedback from the observations. So you see that they're pretty close here together. One thing that changes, though, dramatically is that gas and young stellar regions now decorrelate well. If you only have supernovae in blue, the two branches are pretty flat. If you add the early feedback, orange and green, you get more decorrelation. You get closer to the observations. These small scale changes, this is really at the scale of forming stars, actually changes the appearance and the structure of the galaxy at large. If you only have supernovae, this is the gas, these are the stars. If you add this additional momentum for feedback, now this is the gas, this is the stars. So you can see that we have much smoother disks by adding this early feedback, which means that the stars are less clustered, the supernovae are less clustered, and there is less gas that is pushed out of the galaxies. And this is actually a dramatic change. The gas outflow rate varies with almost an order of magnitude between the case with only supernovae and the case where you have more feedback, but early on, right? So you add more feedback, but you actually push less gas out of the galaxy. And this is because this empirical feedback regulates the star formation, not by blowing out the gas, but just by putting it out of the star formation phase. So have we solved challenge one? Can we now provide inputs to the simulations? Well, we certainly have now a fundamental test of simulations to see if the cloud cycle is reproduced well. I've shown that observations can be used to constrain the subgrid recipes in simulations. And we now have available measurements for 100 galaxies. So this is definitely a good step forward. The definitive test, of course, will be to really quantify this cycle, both for simulation and observations, and see what the differences are and what is the physics responsible for these differences. Of course, as I mentioned at the beginning of this talk, we now have an enormous volume of data. The analysis that I have described sometimes requires human supervision and intervention, which is not ideal when you have so much data. So the challenges now going forward will be to directly trace, without human intervention or subjectivity, this evolutionary timeline, building on the prior observational analysis that we have already done, and using some machine learning analysis algorithms to automate this. So I hope I've convinced you that with these new observations, new analysis tool, we can now constrain or describe the mass flows going through this cycle. And to answer the three questions that I've shown at the beginning, how do galaxies turn their stars into gas? Well, quickly, but with low efficiency. We still don't really know about the cloud assembly time or the duration of the embedded star formation. How do the newborn stars impact the remaining gas? Mostly by early pre-supernova feedback. Which feedback and when remains to be really determined for certainty in different environments, and also the impact of supernovae on large scales. How does this cycle depend on galactic properties and environment? We know that they matter. We see some dependencies, but the exact physical mechanisms are still to be determined. So we still have a lot of work to do. Thank you very much for listening, and I'm happy to take questions.
Thanks very much, Mélanie. I'm sure that there are questions here in the audience, and those online, if you want to, please put your hand up or indicate in a message that you'd like to ask the question, please do so. But let's start with the audience here.
Thanks, Mélanie, for a very nice talk. I have maybe you can explain to me a bit more how you get from the spatial decorrelation to a time scale, because I understand the spatial decorrelation, but then suddenly there is a time scale. Where does it come from?
So let me go back here. So here. So this is the effect of the spatial decorrelation, right? You measure the gas to stellar flux ratio focusing on gas peaks, you have something higher. And when you focus on stellar peaks, you have something lower. That's the spatial decorrelation. Now, to go from the spatial decorrelation to the temporal timeline, this is with this analytical function here. I have not represented the equation because it would take a little bit of space on that slide. But it turns out that you can describe this line here, these two lines are just two equations that are entirely described with these three quantities. And that's all. You don't need anything else.
But there must be some physics behind it, right?
Yeah. Well, the physics behind is that
is the shear of the galaxy, or is there what? Okay.
Right? No. Well, it's we think it's the feedback mostly, right?
Okay.
So you have what is the best? I don't know. Maybe this one here. You have in some regions. So it's really that in different places in the galaxy, you're going to observe regions that are undergoing this timeline, but they are at a different moment of this timeline. So some of them are still gas clouds. Some of them are already forming stars. Some of them have already dispersed the gas. So it's the fact that you see them at different moments. Maybe you can see it the other way around. There is a timeline, and the fact that these regions are appearing are seen at different moments, therefore you have a spatial decorrelation.
So then essentially the cartoon on the right,
Yeah.
that's essentially then a model that uses physical principles to go from gas cloud to star?
You don't need actually any physical principle. You need to say, this is living for a certain amount of time. This is happening for a certain amount of time, which can be 0. And this is then happening for a certain amount of time. But you don't need to assume any physics. It's just, you need to assume that at some point you have gas clouds, and you know that they will form stars at some point. But that's all you need to assume, is that one is transforming into the other.
But do you need to put these timescales in, or do you get them out?
You get them out by fitting.
Okay, thank you.
Okay, thank you. I don't questions online. Another question from the audience, perhaps? Yep, at the back.
And yeah, this is true what Ivan is saying here. The assumption is that the star formation is relatively constant. So this is one of the assumptions indeed, is that, yeah, each region will form stars at a relatively similar speed in a way. But that's, yeah, one of the only assumption really.
Hi, Mélanie. Thanks for the talk. Oh my, okay. I had a question on the scenario for drift when you and dispersal. And so there is a slope at some point, what you expect if in the drift scenario. And I guess to have this slope, you need somehow to have an estimate on the speed at which or do you get the slope?
I thought so at the beginning, but actually when you do the math, the slope is the same, whatever the speed. So if you actually, it's very simple math, and you will see that the speed cancels out. And that's why in that plot here, the slope is always the same. It cancels out, turns out. Negative here. Yeah, so, okay, error bars. That's probably some measurements that we can improve here. Maybe the resolution is a bit marginal to do this test with this galaxy. Because in principle, we would not expect that. Maybe there is an explanation that, yeah, still need to think about that.
Yes, so thank you. Very nice talk. Very nice overview. Still on the slide and on the drift, I can see that, increasing the aperture size works if you have only one region, but this is embedded in, a sea of other regions. Eventually you need to reach saturation, right?
Yeah.
That needs to depend on the locus in the galaxy, needs to depend on the surface density, on the star formation rate, and so on and so forth.
I mean, this is exactly why we stopped. We don't compare through the entire range here of resolution, but only between the size of one cloud and the distance between two regions, the typical distance between two regions. Because indeed, if you start including other regions, then your measurement doesn't work anymore, actually.
Exactly.
So that's why we stop here. This dashed line is exactly that.
And the mean cloud radius you get from the observations and fitting.
Yes. Yeah, we also fit actually directly from the observations.
Okay, thanks.
Thanks very much. If I may, I'd just like to ask a question on the tuning fork diagram, the one where it's stars to stellar mass ratio on different scales. Yeah. I guess you mentioned at the beginning that measuring gas mass is not such a big problem as timescales.
Yes.
I guess you know what I'm going to ask, but if you're looking at these clouds down here they're going to be illuminated in a very different way to the clouds on the top part. So how do you get around the problem of a systematic change if you've got molecular mass in the tracer CO molecule to actual hydrogen mass? How do you get around that?
So tracers are definitely a problem. Here we're looking at a gas in CO. So when I say here that we focus on gas, is that we focus on CO luminous gas clouds, okay? Then when the CO is gone, so for example, here we focus on stars, there is almost no CO associated with them anymore. It's because, yeah, again, there is no detectable CO cloud. You might argue that there is CO dark H2 gas and things like that. Sure, but now we need more observations. We need, for example, C1 observations. Mm-hmm. That would be great.
Yeah,
or directly H2 observations, maybe with James Webb. But again, we need very high resolution and to cover an entire galaxy. So CO is pretty good for that. Yes.
Okay, I see that there is, Hans Ludwig has a question. So I'm going to just release the microphone on this laptop.
Okay.
That. So Hans Ludwig, go ahead.
Yeah, do you hear me?
Yes.
Do you hear me? Okay. Melanie, thanks for the very nice overview. The scenario that you developed holds for the present day universe, right? I have tried to see whether, or do you see, or do you expect that this scenario would also work during early phases of galactic formation?
Yes. Go a bit further away. Yes, so indeed, I've shown only nearby galaxies here because that's where we get the resolution high enough to do that. But we have started already to look at higher redshift galaxies. So up to redshift 1. This is a bit challenging because instead of hundreds of clouds per galaxy, then you see only maybe 5 clumps. So this is quite challenging, but we have techniques. We're trying to develop techniques to go around that. It seems that we see something similar. I can't give you a time scale yet. That would be, yeah. That would be very much of a speculation.
I understand that observationally it's very difficult, but one might have developed now sufficient physical insight and intuition that one might say, yeah, we have good reason to believe it works in the same way, or that there will be significant differences.
Mm-hmm.
I don't know.
Yeah. I mean, I do expect something similar. The size of the clouds, of the clumps, I mean, we call them clumps at higher redshift. The size and the masses of these clumps are thought to be much higher. So I would expect maybe longer timescales in general. Mm-hmm. But yeah, that's, I think, all I can say for now.
Thank you.
Okay, yes, indeed. Thank you. I think we just come to the time where we have to wrap up. Thank you very much, Melanie. That was a really, really very fascinating insight into how stars form and their effect on the interstellar medium. Thank you very much.
Thank you.